One. So I think we can start. Meanwhile, people will be joining, so I will take care of that from my side.
Okay.
Uh, okay. So hello everyone. Good evening to all of you. As all of you know, uh, from last few months, as per our initiative DesignSpire 2025, we are conducting technical webinars with industry experts. Till date, we have organized 3 such webinars in our platform, and this is the 4th one. So today, our webinar topic is on innovative seismic resilient or robust structures. So today, as our guest, we have Dr. N. Subramanian sir. Sir actually required no introduction. We all know sir. He's a uh, uh, renowned structural consultant, an award-winning author, mentor, and obviously we all follow sir on LinkedIn and different other platforms for his mentorship. So today, without wasting any more time, I would like to invite sir to present his presentation. Over to you, sir. Thank you.
Thank you, Engineer Sandip Deb. First of all, I want to thank you for inviting me to give this lecture. Uh, so let me go. Sorry about that
Yes, sir.
hiccup.
No problem, sir. Now it is visible. Yeah.
Now?
Yes, yes, it is visible.
Okay, right. Actually, sorry about all of you. Sorry about the hiccup. Actually, when we design our buildings using our codes, you may think that it is going to be safe, but it will be safe, but there will be some damage. This damage is because our codes are written in that way. So we will discuss about these seismic damages and then the seismic design of buildings, and in that detailing is as important as design. And we will also see some of the seismic moment connections in steel structures which are not covered in our code, robustness versus resilience, and shifting design strategy, resilient designs, increasing robustness through base isolation, energy absorbing devices, and also we will see how to increase the robustness using simple method. And finally, we will discuss about steel plate shear walls and speed core systems, which are used in USA but not used in India. So this famous saying, earthquakes do not kill people, but improper design and detailing do, which is very important, very correct, because in most of the previous earthquakes, we have seen that these collapses have occurred. So here you see this collapse of a building in Burj during the Burj earthquake, and you see this. This is due to the open ground floor, and the beauty of the thing is the building itself has been split vertically at the middle, and at the bottom of the screen, I always put the references from which I have taken these photographs or the messages. Now we will see what are the factors influencing seismic design. Peak ground acceleration, peak ground velocity, ratio of PGV versus PGA, peak ground displacement, which is difficult to determine, amplitude, magnitude and duration, distance between epicenter and site, geographical conditions, soil properties at the site and foundation type and characteristics of the building. So you see that there are so many factors that are influencing the seismic design. And here we see the damage of a steel building in Mexico City in 1985, which is a very important earthquake because the Mexico City is on a soil bed which is very, very soft. Some more damages. This Burj Gujarat earthquake in 2001 killed 20,000 people, injured 1,670,000, and destroyed 340,000 buildings. and the property damage was approximately 4,519 million. This shows two buildings. Both are five-story buildings. They collapsed due to soft story, similar to the previous slide. And here there is a damage due to the short column effect. And as I already informed, during several past earthquakes, we have seen several failures, and some of these failures I am listing it here, and some of them are also shown in photographs here. Shear critical columns, weak columns and strong beams, sudden change in stiffness, planned and vertical irregularity. This shows a um, T-shaped building which collapsed completely. Torsional irregularity, unconfined beam column joints, and then weak stories, floating columns, etc. Actually, in our designs, columns are more important than any other building, any other component, because columns transfer all the loads from top to the foundation. But enough care is not taken in the columns, and several failures have occurred. But they are categorized as buckling of column reinforcement due to insufficient lateral ties and insufficient transverse reinforcement in beam column joints. Of course, that you cannot see, but this is due to the beam column joint failure. Poor anchorage of beam bars in beam column joints, provision of strong beams and B columns, and improper detailing in plastic hinge zones. And this failure is due to this. And this is a punching failure, which is not exactly a column failure, but due to the slab, the thin slab. And I wanted to show this slide always. I have also, you might see this in my book also. This is a building which collapsed during the 1971 San Francisco earthquake. And this building has got rectangular columns as well as spirally reinforced columns. See, this is spirally reinforced column in the first story, that is ground floor. It is still carrying load, though the cover has fallen. But you see this completely collapsed, tied rectangular corner column in the same building at the same story. Of course, these are other failures during earthquakes. This is pounding, that is when two buildings are close to each other. And this is a soft story we have already seen. And then the collapse of water tank. Actually, this, as per our code, all projecting things, horizontal as well as vertical, should be designed for 5 times the design horizontal acceleration coefficient. And this I just wanted to include. This is a recent Myanmar earthquake. This you might have seen because it was viral in social media. This is a collapse of tall building in Bangkok. This is unfinished headquarters of the Auditor General's office, and this is the only skyscraper to collapse in Bangkok. This building used flat slab construction, which is no longer recommended in earthquake-prone zones, in our code especially. Additionally, long slender columns were seen in the ground floor. Probably this Bangkok soft soil could have amplified ground motion 3 to 4 times, and you see this collapsed building like this, completely collapsed. It was a new, yet to be opened building. And when I saw this collapse, I found that there was a punching failure at the top, and then due to that, the last floor failed on the next floor, causing a hammer effect, and then it collapsed immediately within seconds. So now we will see seismic design of buildings. As you all know, there are so many codes in India. IS 1893 is the basic code which is under revision. IS 13920 is the detailing code for concrete structures, and there is only one more new code, IS 18168-2023 for seismic detailing of steel structures, and there is one more code, IS 4326-2013. So we have to, as per these codes, we have to have lateral force resistance systems, and I am showing some of the systems in concrete, shear walls. This is the best system, and then next is braced frame, and then finally moment resistant frame, which we are mostly adopting, which is not very good. And similar things in steel, shear walls, braced frames, and moment resistant frames. For better performance in earthquakes, we should have regular configuration, and hence the best plan will be circular, but it is slightly difficult to build, so we always prefer a square or a rectangular section. But elongated rectangle is bad. Worse is the T section and L section. It is because this re-entrant corner, there will be always be failures. Actually, before doing analysis, the planning is more important in earthquake resistant design. Unfortunately, this aspect is not controlled by us. It is controlled by architects. So whenever you see a plan, you have to discuss with the architect and educate them about the earthquake effects on those plans. So the effect of symmetry will induce torsional oscillations in structures and stress concentration at re-entrant corners, and hence they have to be omitted. Irregularities are to be avoided. They are listed in IS 1893 Part 1. Of course, 2025 will come soon. And anyhow, these things remain the same. Plan irregularities, vertical irregularities. Under that, there are so many other categories you already know, or otherwise you can see IS 1893 for those details. I just wanted to show this building, book. This is Seismic Conceptual Design of Buildings by Hugo Bachmann. It was released in 2002. You can download this book free of cost from the internet in this link. Actually, this shows the basic principles of the seismic design of buildings. Actually, if your architect is adamant, you can even buy this or download the book and give it to your architect to show how to plan the buildings. So this shows a lot of planning of buildings and failures due to improper planning. So as we have already seen, we should avoid irregular configurations like this T-shaped, L-shaped building, U-shaped, cruciform shape, other complex shapes, and then setbacks, multiple towers. Of course, this cannot be avoided, and some clauses are there in IS 16700 for multi-story building that gives more discussions on multiple towers and backstay effects and split levels, and unusually high bottom floor or low story, and outwardly uniform appearance but non-uniform mass distribution. So all these things should be avoided. And the abrupt changes in the plan or also the vertical thing should be avoided. So we have already seen this. Interruption of columns, interruption of beams, and interruption of shear walls, openings in diaphragms, all these things should be avoided. Can we design to resist earthquake with no damage? Yes, we can, but they will be very expensive and unwarranted for the small probabilities of occurrence of such catastrophic earthquakes. Because most of anyone till now cannot say when an earthquake will come and what is the intensity of the earthquake or the magnitude of the earthquake. So our objective is to reduce the probabilities of fatalities to an approximately small level. And hence the seismic design philosophy that is used in IS 1893 is minor and frequent earthquakes should not cause any damage. Moderate earthquakes should not cause significant damage but could have some structural damage. Major infrequent earthquakes should not cause collapse. So that means there will be severe damage. Hence, design is done for much smaller forces than the actual seismic loads. So this is different from the other loads like wind, dead, live and other loads where the exact loads we are calculating and then using it. So as it told, it is not possible to predict where earthquake will strike and its magnitude or intensity. So the philosophy is followed like this. So this is the actual linear response. So due to, and we also always have nonlinear response. So we consider ductility, redundancy and overstrength and then designing for these smaller forces. So one important thing I want to say and insist that we should always reduce the drift. So total drift at the topmost usable floor as per IS 16700 is H by 500. For single story, it is the limit should be relaxed to H by HI by HI is the individual floor height by 400. For design earthquake force, the maximum interstory drift shall be HI by 250. And of course, this has been stressed in many seminars and webinars. Yeah, we should have a strong column and weak beam. And you should not have weak column and strong beam because in this case, all the columns will fail. So this is what I was telling. This concept will make plastic hinges to form in the beams and only at the end the hinges will form at the column base. So once again, detailing is as important as design. For example, this confinement in columns, this shows ties at large intervals and this shows the ties at closer intervals. Due to this, the concrete between these ties is very, actually you also see there is one more tie. So due to this, it is the confinement of concrete is very good. It is important to have closely spaced transverse reinforcement at column plastic hinge locations especially, and to have 135-degree hooks, of course, throughout the column in earthquake zones. And if there is a short column, it is better to provide the closely spaced ties throughout the length of the column and not only in the plastic hinge zones. And this is always omitted because it is very difficult to provide these beam column joints. But these beam column joints are very important. And here also we have this 135-degree hooks which resist the ill effects of the distortion of joints. And shear walls are important. And once again, these shear walls should be placed symmetric and especially at the end of the columns and in both directions. Then only it will be effective. If you provide shear walls like this, it will not be effective. Once again, detailing of shear walls. It is important to have closely spaced transverse reinforcement, spaced at spacing less than 5D, where D is the diameter above in structural walls, boundaries and columns. And I have shown these things which you may know already. And this is a wall failure during the 2011 Christchurch earthquake in New Zealand. And coupling beams are very good in earthquakes for dissipation of energy. And previously people were using reinforcement like this and this. But Professor Santakumar of Anna University, when he was doing his PhD with Professor Pale of the New Zealand University, he developed this system of diagonal reinforcement, which is now adopted in most of the codes. And you see that using this normal conventional reinforcement, failure in these coupling beams during the Alaskan earthquake. This is a 14-story apartment building. Of course, this is 1964 earthquake. So now we will go to see seismic moment connections in steel structures. Of course, these structures are provided, or you can refer to pre-qualified connections for steel SMF for seismic applications. Yeah, IASC 35822. It gives details and design of several connections which have been pre-qualified. That means they have tested all these connections thoroughly, and then they have developed the equations for these connections, and those equations are all provided in this thing. So there are mainly three strategies: toughened connections, strengthened connections, and weakened connections. So the main aim is to shift the plastic hinge location from the beam column joint from to a point away from the beam column joint. So mostly if you provide these connections, the plastic hinge location will not form here, but will form here. So these are the other possibilities: using cover plates, using grips, using side plates. I'll show one more slide of side plates, which is complex, but it has been developed using haunches. This is an interesting Kaiser bolted bracket, which is made of cast steel. This is a cast steel bracket, which can be bolted to the columns. You see an example of a picture of these things, and see how they are bolted to the columns. And this is a composite construction. Actually, the first thing which was developed was the dog bone weakened connection. So where they shaved off some portion in the top flange and the bottom flange, and the radius is given here. And there can be so many different possibilities. One is straight cut, tapered cut, and also through constant holes or increasing hole diameters in order to reduce the area, so that the plastic hinge will form away from the beam column joint. And here I have given some cost estimates. So this is a pre-Northridge welded flange bolted web. If you take it as one, other things are expensive than this, because it requires extra fabrication. So this radius cut dog bone joint is cheapest, 1.71 only. Of course, the relative cost is only for this joint portion, not for the total building. And you see, top and bottom hinge will be the most expensive, because it requires extra fabrication and also extra material. So this is the side plate connection. It is a patented connection. You see how complex it looks, but it makes the beam column joints safe. Now we will see what is robustness versus resilience as applicable to structures. Robustness is defined as the ability of a structure to withstand events like earthquake, wind, fire, explosion, etc. without being damaged, whereas resilience is the capacity to recover and return to full function after experiencing damage from an extreme event, focusing on the ability to bounce back after disruption. Thus, robustness is about preventing significant damage in the first place, while in resilience there can be damage, but recovery is fast. Actually, you may be interested to know that structural robustness criteria are being introduced in the 5th revision of IS 456 and class 9.6. This shows the schematic representation of seismic resilience. You see, initially it is good, and then damage, and then it bounces back to the original thing. So these are the key differences between robustness and resilience. And one is focus on damage. It prioritizes minimizing the extent of damage caused by an event, while resilience focuses on the speed and effectiveness of recovery after damage occurs. So robustness is considered as a proactive approach, while resilience involves considering recovery strategies after an event has happened. So examples of robust and resilient design: a building with redundant structural elements and strong connections to prevent localized collapse in case of an earthquake. Whereas in resilient design, a building with easily replaceable components and rapid repair mechanisms to quickly resume function of the building after a natural disaster. I just wanted to show you a resilient example of a resilient building. I will show one more resilient building later. This is a Empire State Building in New York. It is a 102-story building, 443 2-meter tall, and it was designed and built during 1930 to 1931. A very interesting thing is that it was designed and built before the use of computer software. So you see that they built such a tall building without using computers, because the computer itself, computer software or big computers were not available at that time. On July 28, 1945, a B-25 Mitchell bomber crashed into the north side between the 79th and 80th floor, and the building survived the impact. Of course, this New York is not earthquake prone, but even such things or the building is able to manage. Since 2011, it is powered by 100% renewable wind energy, aiming to achieve carbon neutrality by the year 2030. So we will see now what is resilient designs. The code requires minimum design for earthquake resistance is based on balancing economy and life safety. Structural engineers design lateral systems with certain components intended to absorb earthquake energy through inelastic response to prevent damage. Let us compare the number of fatalities between the 2020 M7 Haiti earthquake, that killed 200,000 people, and in 2011 M6.2 Christchurch earthquake in New Zealand, in which only 180 people died. Clearly, the ductility-based seismic design adopted by our codes is successful at providing life safety. That was the main intention of the codes. But in Christchurch Central Business District alone, more than 1,400 buildings were demolished. At the time of earthquake, the population of Christchurch was approximately 350,000 only. Think about the damage in larger cities like San Francisco, Los Angeles, New Delhi, or other big cities, Bombay, in India. The number of buildings that would be damaged and then require either very long and costly repair or demolition would be much greater. So structural engineers should initiate discussions related to the functional recovery objectives early in the design process. Engineers should clearly communicate to the owners that meeting a code minimum will result in damage that could require repairs that render the building partially or completely unoccupiable for months to years following an event. For example, if a beam is damaged, because plastic, our codes will make plastic hinges to form in the beams. So if the beam has to be replaced, you know how difficult it is. So the functional recovery objectives are critical in selecting the lateral and gravity systems. Different lateral systems we have seen already: shear walls, brace frames, mount frames, etc. have different functional recovery characteristics. Shear walls and brace frames tend to have lower relative storages, but they have higher floor accelerations. Moment frames tend to have higher relative storages, but lower floor accelerations. Both structural and non-structural damage are affected by the dynamic characteristic of the lateral system. Very stringent functional recovery objectives may require the use of seismic isolation or supplemental viscous dampers, which we will see at the end of the lecture. High ductility systems, as advocated by our codes, will incur significant damage in design level or greater earthquakes. The building code ASC 7, for example, provisions that improve functional recovery require designing for higher forces and decreasing allowable drift limits. Actually, you may see in IS 1893, in the next revision, they are advocating for higher forces. These requirements improve functional recovery, but they have cost implications. Strength and stiffness are two controls that structural engineers have that could affect functional recovery, but they are not the only controls available. So now let us see, conceptually see these things. So when you adopt a reinforced concrete shear wall, the flexural shear yielding at the base will occur, so which is very difficult to repair after an earthquake. Whereas if you have a coupled shear wall, the damage will be in the coupled wall system, which can be replaced after an earthquake quickly. One way to enhance functional recovery at little extra cost to use a lateral system with replaceable fuses. So this is a recent concept. And replaceable fuses are designed to absorb earthquake energy in a component that is easily repaired or replaced. We will see how where these replaceable fuses are placed and how to see here. This is a steel moment frame. So as we have seen, the hinges will form during earthquakes, which are very difficult to, these beams are very difficult to replace. Whereas if you have a replaceable fuse plate here and the beams are not damaged, and following the earthquake, these yielding fuse plates only has to be removed, which is very easy. And there is a patented system called Durafuse moment connection, and this although this looks complex, there is a fuse plate which only will be damaged. This is given in ASC 35820. The details of this are given here, and this fuse plate after the earthquake will be if it is damaged, then it can be removed. And similarly, in braced steel frames, this is the normal brace frames. And if you use buckling restraint braces, they can be easily removed after an earthquake. And another thing, another system, it is called rocking brace frames, RBF. And here you see yielding fuse plate are placed here, and it also has a high strength cable. This is a controlled rocking system. Due to this high strength cable, the advantage is it can be self-centered. The damage is absorbed in the yielding fuses on either side of the frame, which are designed to be easily replaceable after an earthquake. So many examples of resilient components have been developed in New Zealand after the 2011 Christchurch earthquake. I have shown some of these systems here. These replaceable frame shear links, and then pre-stressed ring feeder hold down springs. We will see one or two examples of this in buildings also. The key difference is the resilient components as above are integrated as an accessible, replaceable component with sufficient ductility to dissipate seismic energy. Few more systems are shown in the next slide. So compression, tension, yielding, buckling, restraint braces. We have already seen this, and I will show one more slide about this. And compression and tension yielding energy dissipators, and sliding friction joints, and then lead rubber base isolation bearings and concave friction slider base isolation. Actually, they have found out that the cost premium for resilient building design is typically 1 to 3% of the total construction cost, whereas base isolation is more expensive, maybe 5 to 7% costlier than the building without these systems. So on two more systems, or U-shaped flexural plates. Of course, when it is moving like this, the energy is dissipated, and then energy dissipating steel plate connections. So this is an example of this steel plate connection. This is super lot 7 buildings in Christchurch. This is a precast concrete wall where they are coupled with ductile weld plate connectors of 10 to 20 thick. The plates can be accessed and replaced if necessary, and usually they are hidden from the view. All the precast walls in the longitudinal directions are detailed to allow for ductile response at the base as required by coupled wall system by long debonded length of starter plates connecting the panels to the foundation. So the hysteretic energy is dissipated by plate yielding. The plates acting as, so this is the yielded plate. The plates acting as yielding fuse. Each connector is welded to the cast end plates. So this shows the final building, and this is the performance during test. So in the previous thing, in the test, you don't see the pinching, which is normally seen in the poor connections. And this is another building which is having these springs. This is a puny student accommodation building. Once again, in all the 3-4 buildings which I am showing are from New Zealand, they has rocking concentrically braced frames with a ring feeder hold down springs. These are the systems. These ring feeder springs combined with concentric braced frames are designed to rock and uplift at the base, dissipating energy and restoring the frame to vertical. The springs have pre-compression applied to counter uplift forces due to seismic action. In some cases, additional post-tensioning can also be applied to supplement the spring compression. This shows another example of Nelson Marlborough Institute of Technology using post-tension rocking timber shear frames. Actually, this is a timber building. This building was built in 2009 and has all timber multi-level post-tension rocking wall structure combined with U-shaped flexural plates. So that U-shaped flexural plates are seen here. So this also is called as plug and play dissipators. They are mild steel bars which yield in both tension and compression. Actually, these bars are confined by the steel tube. You see the steel tube here filled with grout and epoxy, which is similar to the buckling restraint frames. The dissipators activate with the opening of a gap and are typically used in rocking structural system, providing ductility. The yielding and plastic staining is concentrated over a defined length, only this length, through the use of reduced steel area, which you cannot see here. That reduced steel area is inside these tubes. Another example, this is a two-way sliding hinge joint at the terrace stage 1, once again Christchurch. This seismic energy in this case is dissipated by controlled sliding of tension steel plates with minimum damage to the structure. Now you see this figure, observe this figure. It is designed that the beam is pinned here at the top and is connected to the bottom flange of the web by a unique asymmetrical friction sliding detail, which functions via rotation generated by seismic moments. This joint dissipates energy by opening and closing each time pivoting about the top flange connection. They are rigid under working load, slide under design level earthquakes, and return to rigid connection at the end of the earthquake shaking. The bolts and friction plates could be replaced if necessary, because these are only connections, so which can be easily replaced instead of changing the beam itself. Now we will see how the robustness can be increased in buildings. Base isolation. So base isolation, which will prevent vibrations of the top building. So it is confined only to the bearings. you can have additional base isolation systems also. This is the most significant development in earthquake engineering in the past 35 to 40 years. It provides design profession to the ability to design a building that is operational immediately after a major earthquake and also during earthquakes. So there many buildings are having this system. So I will show some of these examples. So one example is a William Clayton building in New Zealand. That is the first base isolated building. Of course, isolators are available up to 1600 millimeter diameter and around 600 height, and can have 80 shear displacement. The performance of this technology was verified during the two famous earthquakes, that is 1994 Northridge and also 1995 Kobe earthquake in Japan. Even during the 2008 earthquake in China also. For example, a California hospital remained operational unlike other conventionally built structures in the area which all collapsed. Another example of base isolated LA City building, you see this is base isolation. This I already told you that it will cost 5 to 7% of the total cost of the building. Each isolator will extend in any direction to 21 inches. San Francisco Airport International Terminal is the world's largest base isolated building. Or in Christchurch Art Gallery in New Zealand is another example. And I wanted to show one more example from India. This is the latest building, the Indira Gandhi Hospital building in New Delhi. Is a major base isolated hospital building, and it was built by CPWD. The first building was again in Bhuj, 300 bed district hospital with 280 lead rubber and sliding bearings. So there are so many types of seismic isolators. You can see the details in my paper published in 2024. Of course, we will concentrate only on elastomeric bearing and sliding bearing. So base isolators may be either coil springs or laminated rubber bearing pads made of alternate layers of steel and rubber, you see here, and have low lateral stiffness so that they will deform during earthquakes. And this is an example, actual photograph of this bearing. And then friction pendulum systems are shown here. This system is found to transmit lower seismic forces to the structure compared to the lead rubber bearings, but the displacements are proportionally larger. Actually, it moves in this plate, which is a curved plate. Actually, base isolation should not be used in all places, especially with the soft soils, because this is the response during ordinary soil. So this T1 is without isolation, T2 with isolation, so base shear is reduced. But whereas in soft soil with isolation, it is base shear is increased. You may be interested to know that Indian code, there is an Indian code on base isolation. Of course, several codes are available in other places also, like ASCO 2014, Euro code 15129, etc. This Indian code provides guidelines for the estimation of design lateral force and displacement to be considered, etc. Actually, as per this code, very interesting thing to note is ductile detailing of the whole structure is necessary, even in base isolated buildings. Now we will go to see what are the energy absorbing devices. Passive energy dissipation is an emerging technology that enhances the performance of buildings by adding damping to the buildings. So damping is another important aspect. So some of the commonly used dampers are friction dampers, hysteretic dampers, viscoelastic dampers. Viscous dampers They consist of a piston cylinder arrangement filled with viscous silicon burst fluid, which absorbs the energy. Other types of dampers are tuned mass dampers, tuned liquid dampers, and hydraulic activators. The dampers dramatically decrease earthquake-induced motion, less displacement, over 50% reduction in drift in many cases, decreased base shear and interstory shear up to 40% decrease. Actually, this offsets the damper cost and can sometimes even reduce overall cost. This shows the diagram of the viscous damper. So this is a compressible silicon fluid. When this is moved, this silicon fluid is compressed and we get the damping. This shows an example where a building where they are shown, and mostly they are present as diagonal members. This is an example of excellent example of a tuned mass damper in Taipei 101. At that time it was the second largest skyscraper. This one is 5.5 meter diameter, 730 ton TMT, acts like a giant pendulum to counteract the building's movement, reducing the shade due to wind by 30 to 40%. The cost was $4 million. Actually, though it is in this area is exposed to heavy winds, this damper was also found to be effective during an earthquake which occurred in this place. So we now come to buckling restraint braces. This is a damper that was introduced by Takeda in 1976 and deals with the buckling problem of tension and compression steel braces. Actually, the original concept was developed by late B.N. Sridhara of Bangalore. Several other researchers also studied and developed different configurations such as circular core, cross and crosswise core, and linear core. Actually, this is the concept of this. This is a cross core which is put inside a steel tube, and then there is a encasing mortar. This method of construction allows the system to accept axial, compressive, and tension forces which are received only by the metal link. So it is received only by this. At this core construction due to slippage. The other outer mantle of concrete is intended to limit the free bending length of the metal joint. Actually, Professor Sridhar came to my office, of course, 25 years ago, and showed this concept using a steel tube and then a small rod. So once you press the rod, it buckles, but it continues to take the load. Usually in structural engineering, you know that once an element is buckled, it is unable to take further load. But because of the tube, this buckling is restrained by the tube and it continues to take the load. That is the concept of the buckling restraint brace. And from that, they have developed this actual system. So now we will just see how simply we can increase the robustness. Many organizations like ACI, FEMA, NIST have disaster recurrence committees to study the effects of major disasters on construction worldwide and identify potential design issues requiring code changes. Based on 14 different earthquakes in different countries and the ideas of NATO in Japan and Sozen in the USA, it was suggested by Pujol, this paper is listed here, recently, a minimum area of structural walls in RC and structural steel buildings in areas of high seismicity will prevent collapses and reduce structural damage, thereby saving lives. It could also result in increased functionality of the buildings and cities after earthquake, thereby reducing population dislocation and increasing community resilience. So they have shown this building, this graph, after studying 1,600 buildings in different areas of the world. So these red dots are the failures, and the other dots are not failures. You see that this is wall index, this is column index. Wall index is smaller of the areas of walls in two orthogonal directions plus 1/10 of the area of the masonry infill walls, and then to the total floor plan area. Column index is 50% of total column area by total floor area. You see that most of the things are confined here. So only some 7 failures are above this. So separating the data by earthquake site does not change the conclusion, which is remarkable given the different areas that are considered, not only in USA but also in different places. So another correlation with the priority index is equal to wall index plus column index. So you see that in Turkey it is very bad, 70% of the damage, whereas in Chile, actually in Chile, a lot of buildings are built with structural walls. There is a strong correlation, you see, between damage and this index, priority index. So based on that, the minimum area wall, the absence of rigorous field quality control and exhaustive testing, adopt structure walls areas as below to get robustness. 0.2% into n, where n is the number of floors. So for buildings for less than 15 stories, of course, detailing is critical to safeguard against larger ground motion intensity and drift demands. It is better to lower drift demands to about 1%, as deformation drift can damage partitions, facades, and finishes. It will also result in increased functionality of buildings and cities after earthquake. Actually, in taller buildings, wall intensity of 3% of the floor area in each direction is sufficient as per Chilean tradition. Actually, you may be interested to know that 2% has been stipulated in ISO 1893-2016 for RC framed buildings with open stories. So finally, we are going to discuss about this two more systems. One is a steel plate shear wall. There can be three different types: unstiffened, stiffened, and also composite concrete SPSW. This shows the example in Quebec, Canada, in a 6-story building. This system has been recognized in the National Building Code of Canada since 1994 and also in the AAC since 2005, and provisions are available. This shows horizontal, that is SPSW in Japan with horizontal stiffness. Here, horizontal stiffness as well as vertical stiffness. The advantages of this SPSW: if detailed properly, up to 4% drift without damage, thinner walls, actually less structural wall thickness compared to RC shear walls. The average wall thickness of Century project was 450 mm as opposed to RC shear wall of 700 mm, saving of 2% in gross square footage, and it is lightweight. Lower building weight reduced the foundation and overall building seismic loads. In the Century project, the total weight was 18% less than the RC shear wall core system. It can be welded, field bolted, no curing time. Construction easier than concentrically braced frames. Actually, the Century project 1 month reduction was achieved. At least 2 buildings using SPSW as primary lateral force system have undergone significant earthquake ground shaking and found to be effective. Easy to retrofit. Of course, there are some drawbacks. They are more flexible. Excessive initial compressive force in the steel plate panel may delay development of tension field action. This tension field action is similar to the plate girders. In the US Federal Courthouse project, Welding of the steel plate splice connection was delayed until most of the dead load reformation occurred to relieve the pre-compression within the steel plate shear walls. Of course, because it's a new system, the contractor may estimate higher erection costs. This may be solved by engaging contractors early in the design process. These are some examples of the buildings which have steel plate shear wall system. The Kobe office building survived the Kobe earthquake in 1955 with minor damage. Actually, this Seilmer hospital went through Northridge earthquake in 1984 and survived without any structural damage. However, there were wide-ranging non-structural damage. Of course, you can have some openings also. So it was tested by Professor Bruno and his associates. This shows another stiffened, shear plate, steel plate shear wall with openings. So they just tested for his Vian's PhD thesis. Another innovative composite steel core system, which was developed by Magoonson Clementic Associates and Professor Verma and also Professor Bruno. This process tested the system in their laboratories. This consists of a steel plates. See, these are the two plates, and which have the tie bar so that the two are connected, and there can also be a side plate, and then there are these shear studs. So the composite interaction between the steel plates and the infill concrete is developed by the tie bars or by a combination of the tie bars and the shear studs. This is a composite speed core system. Actually, the empty steel module consisting of steel plate, tie bars and shear studs are prefabricated in the shop so that the quality is very good and shipped to the site for final assembly and concrete casting. The empty modules are stacked to a certain height, typically 2 to 3 stories. We will see the next slide about that. For each placement of concrete, and the process is repeated as the structure is constructed. The steel plates act compositively with the hardened concrete, and the tie bars this is tie bars or steel studs, shear studs. They are acting as anchorages. These regularly spaced steel anchors and tie bars restrain local buckling of the steel face plates, provide horizontal shear resistance, and develop composite action between the steel plates and the concrete infill. So here you see, this is how it is constructed. And this is the first example where this thing is used. This is the actual completed building, and this shows the central tower with the system. This building is in Seattle. The advantages are speed of erection, cost saving, increased strength, increased blast resistance, and flexibility for adaptive use. Actually, code provisions were included in the AIC 36022. Actually, it designed the non-seismic applications, Chapter 1, Fire Resistant Design Provisions, Appendix 4. AIC 34122, Section H7 addresses seismic design. A new Section H8 will cover capacity design principles, limits on the applicability of coupled speed core, and other detailing requirements. Actually, a new design code guide 38 has also already been released. This is another example. I told you that I will show another example of the robust building. This is Torre Latino Americana building in Mexican City. This was built in 1956 with a height of 188 meters with 44 stories. And this was designed by the Mexican engineers. and then proof checked by Professor Nathan and Newmark at the University of Illinois. Actually, this building withstood Richter 7.9 earthquake in 1957 and also another earthquake in Richter 8.1 earthquake in 1985. Actually, the people in this building saw the other buildings nearby failing, and still this building withstood those earthquakes without any problem. So I just wanted to touch upon the smart building technologies and adaptive materials. This SMAS, for example, nickel titanium alloys are advanced materials with the unique ability to return to a predefined shape after deformation when exposed to heat or stress. Their super elastic and shape memory effects make them highly beneficial for earthquake resistant and durable reinforced concrete structures. Actually, these things are under research. So probably soon they will be adopted in future buildings. So this I just wanted to show. This was this was reported by Marius Pinkwala. In one diagram, he has shown what are the different things to be adopted in earthquake resistant design. Avoid soft stories, control torsion, design stiff foundation, etc. So I just wanted to show to you. So you can visit that LinkedIn site and to see this thing. So finally, let us summarize what we have discussed till now. Buildings with regular configurations and symmetric shape without irregularities are better in seismic zone. As per seismic design philosophy in codes, only a percentage of the earthquake load is considered using the response reduction factor. Once again, I just want to tell you that R factor used in the codes are not systematically developed. They are all based on engineering judgment and previous experience. Hence, during strong earthquakes, the structure may be damaged but will not collapse. So AAC 35822 gives details and design of several pre-qualified connections, which will result in better performance than ordinary connections. Resilient design is required for the functioning of structures after earthquakes. Examples of resilient buildings are those with incorporated special connection detailing, supplemental energy dissipating devices, rocking systems, and base isolation techniques. Of course, the technologies include structural fuses, innovative dissipative plate connectors, sliding hinge joints, etc. So I have already shown some example buildings using these systems. So extra cost is 1.1 to 3% in the systems which uses these systems, and the extra cost will be 5 to 7% if it is base isolation. Robust buildings are rigid buildings having natural period less than 0.1 second, which may not be affected much during natural disaster. And we found that structural walls is about 2% area in buildings less than 15 floors and 3% in buildings greater than 15 stories were found to be robust. Some authors also suggest H by T ratio to be greater than 45. T is the H is the total height and T is the time period of the building. Base isolation allows isolation of building from earthquake ground motion. Various types of base isolations have been developed and you have seen some of them. IS 1893 Part 6 provides guidelines for base isolated buildings, and energy absorption devices can be used to mitigate the effect of wind also. Innovative systems such as steel plate shear walls and speedcore systems can reduce the seismic damage. Thank you very much for your patient hearing.
Thank you so much, sir, for this
You're welcome.
detailed presentation. Now we'll try to take few questions from our audience. I
Okay,
think
if
we
I
have
know, I will
already,
answer.
yeah, we have got one question from Miss Yamini. Can you highlight major difference in detailing of seismic structures and normal structures? I mean, I think you're asking about seismic resistant design and normal design. The detailing differences?
Yeah, detailing is that is of course it is given in IS 1893 and also I think 13920 in concrete for concrete structures. For steel structures, I told 118 the new code 2003. I just forgot the number. So mainly we should provide um, ties at closer intervals near the joints as per the code in the beams as well as in the columns.
Yeah.
That is one main thing. And if it is I have shown in the slides already, that is if you have short column effect, then the ties should be uniform throughout, and the formulas are given in the codes how to
Yes.
find the diameter and also the spacing of those ties. Of course,
Yes.
as I have told in AISC codes, the better thing is to move the plastic hinge location away from the joint. That is very important.
Yes.
That is why we provide this this ties also. These ties will strengthen that the areas near the joint so that the plastic hinge may not form at those locations and it will form away from the joint. That is a very important thing.
Okay. Next, we have one question. Is there any concept of shear column or shear wall can be called as shear column?
No, shear wall only. There is
Yeah.
no shear column. And actually, I wrote a paper about these columns. Actually, the columns are the most abused structures, elements, structural elements anywhere. For example, when you are curing, we are curing the beams and slabs properly by provide. Of course, many places they are also not cured properly, but at least by ponding over the slabs, we are curing them properly. But how these columns are cured? Actually, the column that formwork is removed after 1 day. That means there is no provision for that column
Yes.
for curing, and simply they will throw some water on that. Actually, actually, it has to be properly covered by sacks, and then water has to be cured. Water has to be poured on them, but I don't think that many people do that. So one, and also in some place, in of course, since we have concrete buildings in India, I am only talking about concrete, and and the formwork is high for columns, and we don't vibrate it properly, the columns. So once they remove the formwork, you will see a lot of honeycomb in the in the column, and at the site immediately they will put some plaster and cover it. So those are all not good because we are weakening the columns, and also many in some places they will provide some rods projecting from the columns, but while measuring the plan area, they will find that it is offset. The foundation is offset by some distance. They simply bend the bar and continue the column rods. So that will result in extra bending moment in the column. So those things are not considered. So we have to be very careful. And many places they don't even some, of course, not in many places. In some places they don't even consider the bending moment. So those are all very bad because columns are the most important elements in any structure because they only transmit all the loads from top to bottom to the foundation. So you have to consider them properly. And also it is better in earthquake zones, it is better to have the columns for four floors continuously of the same size. So these are all some practical things many people don't follow.
Yeah. Uh, we have one question from Mr. Mohammed Mustafa. How much can we design a robust uh, building by adopting ground-based isolation methods like open trench or field for structure?
What is the final thing? Open crane?
Uh, Open trench or field. I didn't get what he meant actually. Ground-based isolation methods like open trench or field for structure.
I don't know what it is.
Yeah,
But
I'm not sure. Yes, sir.
but there are many base isolation systems which can be used. Of course, I have shown one or two buildings in India which has been used, which have used this base isolation system. They are very effective. So you might
Yes.
have seen some videos of hospitals in Turkey that were operating during the earthquake also, because the base isolation completely isolates the building, top building, from from these earthquakes. So it is captured only in the base isolation system only.
Yeah. We'll take one more question, sir. The question is from. Uh, so the question is for shear wall, for steel shear wall, how connections are being made rigid?
Yeah, it is to the it can be bolted or even welded, similar to any steel element. And the details will be found in the AAC code. Of course, our code does not have this now.
Okay. So
Actually, you may
yes,
be
sir.
interested to know that this IS 800 new revision has come, draft code. So last date
Yes.
of sending comments is on 18th. There, they have got two appendices. One appendix is for curved webs of plate girders, and then another is for anchors, which was very required, but not found in Indian codes till now. It was only we used to refer to only ACA 31819. Previously, it was in the annex, and now they have included in the main code itself. But now it is good that IS 800 draft code has that in appendix. Of course, I have not seen. I think it mostly follows the ACA 318 code provisions.
Okay, so we do have many questions, but we are running out of time today. So we'll be stopping here for today. Thank you
Okay,
so
thank
much,
you very
sir,
much.
for your time and this amazing presentation. And thank you to everyone who have joined this session today. We'll keep trying to, I can say, get such sessions for you from the industry experts. And thank you again, sir, for
Thank you very
giving
much.
your time today. Thank you.
Thank you.
Thank you.
Thank you
So
very much.
we are closing our event today. Thank you.
Okay. Sorry for the initial problem.
No problem, sir. It's fine.
Okay.
Totally fine. Thank you so much.
Okay, take care.